to listen to this exciting new project that we are trying to do with the collaboration between the Lima Intermediate, starting off because you are the first ones who we did a conversation with and understood what we are trying to do. So we're going to give a demonstration of our backpack-based filter system. First I'll do a presentation. It's going to be like a 15-20 minute presentation explaining like how water ties up with the as a grand challenge for engineering and how we can bring it down to a public school level and maybe make kids excited about doing some water related projects in the classroom and build some activities around that. Presentation to be about. So our topic, of course, water, a grand challenge for engineering. In engineering, when you think about engineering, mostly people think, okay, it's building smart robots, it's like, you know, working on airplanes, but if you go to a certain environmental engineering lab, you'll understand that clean water is also a very, very challenging aspect of engineering, and to obtain clean water, what the science that goes behind it, the amount of like filtration techniques that there are out there are like just enormous. And that from if you talk to an environmental engineer, if you talk to me, my background being electrical, I will say, yeah, you know, I go with gadgets. Talk to Dr. Ray, you'll come back convinced, I'm sure that, okay, how much challenges these guys face on a day-to-day basis to obtain like clean water, which like sometimes people take for granted. Okay, you open the tap, you're getting clean water, you don't think what goes behind it to get it to you. So then, just to begin, Clean Water Challenge, access to clean water is recognized as a grand challenge by National Academy of Engineers, one of the 14 challenges that they are recognized in the United States. Access to clean water is one of them. As we all know, it's needed for environmental sustainability. Clean water is needed everywhere. And production of clean water is expensive. I mean, on a normal perspective, as I said, people think that, okay, not much goes behind it, but the amount of filtration techniques to get it raw or groundwater to a level which is going to be acceptable for drinking water standards set by the EPA takes a lot of work, and that makes production very expensive. So the challenge in a nutshell is to make it faster, to how to produce clean water at a fast rate. The water should be portable and should be readily available to the masses, to the consumer. So that overall is a grand picture. So where is it needed? I mean, as I sat down to think about where we would need clean water, drinking and personal use, number one, of course, irrigation, industry, environmental preservation, and disaster relief. So if you think about it, I mean, not an event in everyday life you can go without having access to clean water. So it becomes a global challenge in that respect. And as I talked about the project that we developed this system for, that's a humanitarian assistance and disaster relief project. So as you can see from this picture here, you know, in countries like Thailand and Indonesia, where like there are natural disasters that are a very common event, you know, in those kind of times of crisis, I mean, the production of clean water kind of shuts down. So you need to give the general population certain systems which they can readily set up on their own, and with least amount of training can get access to clean water until the systems have been restored to provide the continuous production of water for them. So that's the challenge that we are facing in our project. Water facts, this is just an overview. So as we all know, 2/3 of the planet is covered with water, so we take it for granted that water is everywhere, so why is it such a big deal? But only less than 3% of water is fresh water, and 69% of that fresh water is in form of ice caps and glaciers. So what we are left with is 30% of fresh water is the groundwater, and we need that groundwater for 25 to 40% of the drinking water needs. So you can see 30% of the 3% is supporting about 45% of the drinking water needs. So it's not that the accessibility is everywhere. It's very, very challenging to get groundwater resources and then filter them to make it potable. Contaminants, this is just an overview of what kind of contaminants we find in water on an everyday basis. So these are natural and man-made. On natural contaminants, pathogens such as bacteria, viruses, parasites such as protozoa are present in water. And when you talk about man-made, you have to talk about fertilizers, pesticides, heavy metals contaminating the groundwater, and that becomes a challenge. So then, what is needed? What is needed is to treat this contaminated water by effective means, by effective technology, so that it gets to a level which meets the standards for potable water. And that is the challenge for us as engineers, to come up with solutions which can make this contaminated water potable. This slide is giving an overview. I didn't want to go into too many technical details about it, so I just kind of categorized on what kind of filtration techniques are available out there. So water treatment methods can be categorized into these particular categories. Coagulation or flocculation is pre-treatment of water. So before we even send it to like actual water filtration systems, we want to pre-treat the water, because you don't want to block the filters very fast. We have sediment filters, carbon filters. If you are sending out without any pre-treatment, there's a high chance that your filters are going to get, what's the right word, Lucas? Clogged, yeah, thank you.
I thought overwhelmed or?
Yeah, overwhelmed or clogged very fast, and for that you want to do some pre-treatment. So coagulation is a good method. You add alums to the water, which kind of settles the sediments. So then you take the top layer of the water and then feed those to the filters, so that your filters can have a longer life. Filtration systems, of course, the treatment by passing through a granular material that removes or retains contaminants. So the sediment filters that I'm talking about, carbon filters, fall into these categories. And as I move forward, I'll show you what each of these filters are responsible for doing in terms of treatment. Membrane processes, I guess this we all are very familiar with. I mean, I'm not sure how many of you, but have a reverse osmosis system under your sink in the house. That reverse osmosis system has an RO membrane, and that's the very fine membrane. The membrane that we have been using in our RO systems is 0.0001 micron rating, which allows very, very few particles to pass through, so it kind of takes care of a lot of contaminants, sediments, and even pathogens. Chemical disinfection is used to remove pathogens such as bacteria and viruses by adding certain kind of chemicals to the water, which can then kill those bacteria and viruses and then make the water potable. Absorption and ion exchange. And then finally, the solar treatment. Solar treatment is like, use of solar energy to disinfect and distill water, like solar pasteurization. We have these solar pasteurization bags. You fill them with water, leave it in the sun. Once the water changes the specific temperature, it kind of like provides solar distillation and kills certain amount of, but it's not, obviously one method is not 100%, so we have to use a combination of them to make sure that the water gets to the level that you're actually deemed acceptable for drinking. So now my challenge was to connect the dots. I mean, what is the STEM connection with water? I mean, when you say STEM, how the water relates to each of these categories of science, technology, engineering, and mathematics. So the way I thought of it was that for science, the study of level of dissolved oxygen, like the water quality parameters that we are trying to test here, dissolved oxygen, pH, chemical contamination, all those will fall under the science category. Okay, we are trying to study what these parameters mean, how do they affect the water, and why do I need to have these particular water quality parameters at a certain level to make it drinkable. Technology, when we talk about technology, it's always like gadgets to check whether the water quality is deemed safe or not. And there we need the sensors which are going to detect whether the pH quality in the water is okay or not, whether the turbidity is at an acceptable level or not. So that's where the technology comes into the picture. The math, the study of the water quality test parameters and analyzing that data that comes out of it, and what standards have been set and what data you're looking at, whether it's meeting the criteria or not. So that, I think, can be a relation to the mathematics side of it. And of course, finally, engineering. So when it comes to engineering, it's always designing something. And designing of the actual water purification system to meet these requirements is where I think the engineering aspect comes into the picture. So that's how we try to relate STEM with the water.
For the math part of it,
yes.
You already have a template that my students and we could use that would set up to make it a scientific study, so that we're not at random, say at 10 o'clock every day we go out, or make it at 10:05 and we check every, you know what I'm saying? Is that something we've got to develop?
No, actually this is the collaboration, because we collect the data and it's required. So the idea is, if that's an interest, and that's why we put it in this where it's all integrated, is we take that, we sit down with you and say, this is the kind of data, this is the kind of calculation, how can we bring it down to the very basic and keeping the integrity of the process. and then match it with whatever level, you know, even if it's addition, whatever it is,
Or it
whatever.
might just be a regular spreadsheet that my
right,
students take their
right.
laptops out and
Yeah.
they're just recording at that moment. Somebody's with the probe saying, okay,
Right.
Mrs. Zuran, this has a pH balance of block, and so we're data collecting
Mhm.
and then we'll spit it out somehow.
Mhm.
And then we look at it, spreadsheets and that kind of
Mhm.
stuff. Okay, sounds fun.
Yeah, because actually under that project with the Apex and the backpack, we have tons of required EPA. So we can maybe pick one or two of it, and then
Oh,
so
yeah,
you can
just
relate
focus
it
on that.
back, and then incorporate whatever math benchmarks or whatever they need, and you know, kind of
Yeah.
as best as possible align it.
Okay, thank you. Sorry.
Yeah, no, I'll show you some sensors that we have too, which we have there for sharing, and then you can see that how we can collect some of the data using those. And I agree with that part of the, like, creation of a template where, you can set certain parameters and then the students can fill out the information on a daily basis on how they're testing the water quality. Just wanted to give you guys some examples of the existing schools who have been doing, I mean, not really with this system because we haven't introduced to any of the schools, you were the first ones, but because we have these water quality testing sensors from Vernia and also Pasco, so some of the schools had borrowed those sensors and had created their own activities, Dole being one of them. So what we want to show is the diversity with which the schools applied these water concepts in their classrooms. Second example we put was that of King Intermediate, which kind of set up like a research laboratory within the classrooms to do water quality testing using certain simple, I think these are those pH kits that they're using out here. So the skills that they said that the students developed by doing these kind of activities was using online resources, the behavior of predicting, observing, recording and analyzing data, and discussing results amongst their peers on how they are collecting the data from the different water samples and then like reporting their results. So it's kind of a research laboratory environment. And the third one is the Kalakaua Middle School, and this is an example of the aquaponics units that they set up in their classroom. So we've just shown different stages of how these aquaponics units help develop certain characteristics or traits within the classroom. So like preparing the systems, collaboration among students, contributing to the actual project, and then production of the plants at the end. So it's like kind of a stepwise development of the students on showing how these integrated projects work in a classroom environment. So now to the good stuff. So this is the two systems. I put my other system here too. So these are the two systems that me, Lucas, and a couple of engineers worked together with Dr. Ray to develop for this R&D project that I was talking about. So backpack-based multi-level filter, and this is the system that we have in mind for use in the classrooms by Lima. The whole idea of this system was that how can we miniaturize the whole concept of water filtration in a disaster relief scenario, because you don't have the transportation, maybe the roads are damaged, maybe the dams are not available to supply the water. So how do you provide a miniature system which we can easily transport to the local population and they can use for their everyday use at least till the utilities are restored. So for that, the idea was to make it as small as possible and weight efficient so that a person can carry it around easily. So the idea was to put the components in a backpack so that the person can carry it around. The weight of the system is very reasonable. It's like about 12 pounds, so it's easily, you can put it on your shoulder and take it around. We tried to put we succeeded. So three water purification stages in this particular filter. The first stage is the sediment filter, which is going to take care of your bigger particulates, the sediments, rust, and those kind of things. The carbon filter, which is a carbon block filter, rating is 0.5 micron. Is that right, Lucas? Right? And that takes care of your odor and taste. And then we put a UV system at the end. You cannot really clearly see it, but I'll demonstrate it later. So it's a hand-cranked UV system. So this water purification system works on a batch processing. So you take like about a liter of water, of dirty water from a stream, from a pond, feed it to the system, and then the UV unit has this Nalgene bottle about 1 liter in size, and you fill that up, and then you have to hand crank the system. So the reason for doing not a battery operated UV was that you want to stay away from external power sources as much as you can in a disaster scenario.
Because it's not dependable.
It's not dependable on anything, so you don't need any external power source for this particular system. As I said, removes taste, color, odor, sediments, and the microbes. That's the last stage. The UV takes care of it. And produces up to 100 gallons of purified water per day, which is a lot if you think about it. I mean, but the only caveat in this thing is it's a batch processing unit. So the amount of water you produce actually depends upon the individual. So how much you feed through the system, and then how much you can crank and produce. So based on the requirement of a small family, of a small community, you can produce like different levels and different amount of water. So really very successful. I mean, we demonstrated it to the military and we got some very good responses from them. The second system I just wanted to show you guys that take it in another direction, and this is, if you have seen a reverse osmosis unit used in normal households, this is exactly the same unit. What we did was we retrofitted it into a Pelican case so that a person can carry it around easily. This particular system is also for fresh water. It has 6 stages. It has sediment filter, there are 3 carbon filters involved, and then there's a UV unit at the end. And it's completely safe. I mean, the testing that we did with this system also, because of the UV presence at the end, takes care of, meets all drinking water standards that was set by the Thai military, and was really another successful unit too. In production wise, this one, the rating for this system is about 45 gallons per day, so it's a little lower than the backpack system. But as you will see, even to get to that 100 gallons a day for the backpack system, you really have to put in like a bunch of effort, because the UV system is hand cranked. So it's kind of a batch unit. These are the 2 systems. We'll do a demo of the backpack later.
What would you say is the cost of that? Both systems. If you
Okay.
had to put a dollar sign on it.
It's kind of subjective in this case, because we have to factor in the labor cost in it, because our experts
So
worked on
then
it. So
factor in
yeah,
that labor cost.
if you're just talking purely about parts, then the backpack system parts are about like $200. Okay, and the UV unit parts are about like $400. Okay, but once you factor in the labor, of course, the cost goes up. So realistically, the RO system per unit cost is about $2,000 to build, and the backpack around like $1,000. But that's factoring in both parts and labor then. But purely on a parts perspective, that's also an advantage, because the replacement of the filters, these filters are very, very cheap. So the sediment carbon filters that we are using in the backpack system, the sediment filter is about like $3, and the carbon is about like $7. So once they are done, it's very easy to replace. It's a low-cost solution for providing a answer to a disaster relief scenario for a small community.
I just wanted to know, how does this relate? You know that the Puree system, or whatever that system for the water filtration, does this have more filtration units than the one I have at home? You know, that the kind that you buy.
You mean
that's
the
so
RO
expensive?
unit?
Yes. Does it
Yeah.
go through like more?
No,
You know?
it's exactly the same.
it's-
So that's
But
where
they're so
I would
expensive.
like to say where Ben's idea came into picture, because he thought about it like, okay, we want to talk about a disaster relief scenario. I mean, we don't have power, but everybody is using these RO units at home. What is the caveat? You have to plug it to the power.
That's cool.
So he takes that system, he puts it into a Pelican case, and how we are using, what do we do with the power? We are actually using a bicycle pump to pressurize the system and force the water, because power is needed to force the water through the system, right? So to take that away, the power requirement away, he built he used a bicycle pump, retrofitted a container which can now take a valve, you can connect it to the bicycle pump, you pressurize the system, and that's how the water flows from the source to the output level. And that's where you take care of like the power, you don't need any external power now.
Right.
And so that's where the design aspect came into the picture, like how do we get away from power?
And if you did have, say, the car battery, he has retrofitted where you have different options.
Yeah.
And you can recharge based on the solar panels.
Solar
So, he has all the what ifs.
Yeah.
And you're looking at what is easily attainable in these third world countries. Car batteries are, you can get. The solar panels are small. It's looks like a folio, and it just trickles back in the power, so it keeps it going. Yeah, so it's.
This one, we wanted to show you the design evolution of our backpack system. So we've been doing this demonstration now, which I mentioned to the Thai military, for 2 years in a row now. So for the first year, this was how our backpack system looked like. Okay.
With the UH logo on it too?
Yes, of course.
Yes, Hawaii. Good.
PR and advertisement is a part of the game. So this is how we evolved the system first. So what we did was, it was a modular system. So each of these compartments can unscrew and open up, and you fit the system, the sediment filter in there, carbon filter in there, and this was a UV disinfection unit. Now, as we did the testing of the system and took it out there for field testing, we realized that when we pressurize the system using the bicycle pump here, there is an overflow of water. So water starts flowing from, leaks through these compartments into the subsequent compartments without having enough contact time with the filters. And that we realized was a design flaw and was kind of like not giving enough contact time to the filters, overflow of contaminated water from one compartment to the other. So our samples were getting contaminated and we were not getting clean water. So that's when, again, Ben comes into picture to redesign the thing and think how we can eliminate this problem. So to do that, he redesigned it in a separated compartments. So there is no chance of an overflow. So it has to go through one system. There will be enough contact time. We can control the pressure, how much you're pressurizing.
And if there is an overflow, it just flow out into the ground.
It is. There is an overflow. I think there is an overflow valve in this system, but if not, then the way is that it just flows down to the ground, as you said. I'm not really sure. I have to check now that there is an overflow.
No, I didn't mean to.
No, that's fine. No, that is correct actually, because we did that too when we filled up the system to the core, because one of the Thai commanders wanted to test it with overflowing. So that's when the water started just seeping out of the top. So it was like, it's not going to contaminate your next sample or the next compartment.
Right.
That's the important part here. And then we added a new UV unit, and the reason for that was this UV unit had its electrical components at the top. So water started seeping into the electrical components, and then the UV unit itself stopped working. So that's when we replaced a battery operated one with a hand cranked one, so that there is no chance of like any leakage or external power source also, which solves the other problem of not needing any external batteries or powers. So this is like how we as an engineer think on evolution of designs. So kind of gives an example of what are your system flaws, how you did not meet the objective, what needs to be changed to meet the objectives, and a design evolves. Okay, so here I have the inventory of, we have a bunch of water quality sensors in our RET inventory already. So as I said, there are two different categories. One is those Vernier sensors. So we have all these GPS, pH, dissolved oxygen, temperature, turbidity sensors with us. A lot of schools have borrowed these sensors from us on a regular basis and have been doing activities around them. Then Pasco sensors, this is where it gets fun. So the Pasco sensors work in coordination with your iPod or your, I'm pretty sure it can work with an iPad too. And so this one, we gave some schools iPods, and they connected their Pasco sensors to them, and you can analyze the data on these iPods now. So this makes life a lot easier to go into the field and take these iPods, gather your data there, and then bring it back to your computer.
Skills.
Yeah.
Plug it right in and do it now.
Yeah. I don't know if they've been doing with the iPads, but we have tested it out. It works with the iPads and iPods, so there's no problem out there. So it kind of gives you an added dimension on the sensor side to use these cool gadgets as much as with the trend with the iPods and iPads. What's better to get students excited about science or like
technology is right on their forefront.
Yeah, you're gonna collect your data on your iPod now. Take these sensors. So that's like, so these sensors, we have a bunch of them in our inventory. If you guys think that you could use them in your classrooms, feel free to loan them from us and develop your activities using these sensors. Okay, this is coming from my brain, and obviously if you don't agree, you can tell me. If you have other ideas, feel free to go in that direction. But what I envisioned was one simple aspect of using the backpack system on a field trip. So a freshwater source like a lake, pond, or stream, so I used the Dole's example out there. Use our backpack system to purify the water, use our sensors to do a pre-testing of the system, to see the water quality before you have actually done the filtration, and record that data, then use the backpack system, obtain the purified water, and do the testing again. And then you can have a simple comparison of results on how effectively your backpack system is purifying the waters. Yes?
I was even thinking, just hearing you say that too, even like you were saying before, modularly, you could look, okay, how does it look after the sediment filter? And then they take that, those first samples, like look at the turbidity or the pH, and then they put it through the carbon filter and they go, oh, the pH changed, why did the pH change, and then something like that, where they kind of stepwise can learn.
That's a great example actually, yeah. at each stage you can take water sample before and after, and then see what effect that specific filter is having. So yeah.
Mhm.
Yeah,
So
one
it's
of
very-
my students we're doing the water cycle right now, so they were actually asking, oh, how does like a purification system at home or whatever compared with like let's say bottled water
Right,
or
right.
something like that? I mean, maybe they could do like a comparison between, you know.
Between the two,
Yeah.
Absolutely. So yeah, set up an experiment, collect data, analyze results. 3 simple steps, but gives a really good activity to engage the students. This is just general discussion. So the vision that we thought we have for this thing, use an actual university R&D project, which is our Apex project I spoke about, to foster a collaboration between the university and public schools, and see if we can take it forward from there. Engage the students to understand the real world challenges, that water is a real challenge, how are engineers at UH dealing with it, how about you learn about it and come up with some ideas. That the students have brilliant ideas sometimes. I mean, see if you can actually come up with a sophisticated method of purifying water. Provide a platform for UH experts to work with the teachers and provide feedback in setting up the new curriculum, lesson plans, or activities around this particular water challenge. That's how we envision this going forward. That's all I have, so if you have any questions.
I guess my question, what